Well, this is part one of a three-part video series on temperature and thermodynamics. So, in this part, we're going to look at what temperature means, conversion of the temperature from one scale to the other. We'll look at linear expansion and then specific heat capacity, latent heat. We'll also discuss conduction and radiation. So that will be in this first part. So what is temperature? Temperature is the average kinetic energy of molecules of a substance. That means as heat is given to a substance, like the molecules of a gas, they start moving faster. When they start moving faster, they have greater kinetic energy. In fact, it's only at absolute zero or 0 Kelvin that all molecular motion stops. At that point, there is zero kinetic energy. And that's at absolute zero. At all other temperatures, the gas molecules have kinetic energy. So temperature is the average kinetic energy, or it is the measure of average kinetic energy of the molecules. Now, when we take the standard, in order to define the temperature scales, the standard is the triple point of water. And the triple point of water is that temperature and pressure at which the three phases of water, namely ice, water, and steam, or water vapor, ice, water, and water vapor, they coexist. So it's that pressure and that temperature. It's actually 273.15 Kelvin. That is the triple point. So when we define the temperature scales, we consider the freezing point of water, as you can see here, the freezing point of water, which more correctly is the triple point, taken as 273.15 on the Kelvin scale. That is 0 Celsius on the Celsius scale and 32 on the Fahrenheit scale. The boiling point of water is 373.15 on the Kelvin, 100 Celsius on the Celsius scale, and 212 on the Fahrenheit scale. So clearly you have 180 parts here, 100 parts both here and here. So when we try to change from Fahrenheit to Celsius, you have that ratio of 180 by 100 coming in, and that ratio happens to be 9 by 5. So that's why you will see that when we change from Fahrenheit to centigrade, or centigrade to Fahrenheit. So here are the conversions. To change from Celsius to Fahrenheit, multiply with 9, divide by 5, and then add 32. But when we change from Celsius to Fahrenheit, first subtract 32 from what is given. That's important. First subtract and then multiply by 5, divide by 9. To change from Celsius to Kelvin, just add 273.15. Usually we only add 273, which is okay. And from Kelvin to Celsius, you just subtract 273. Now Fahrenheit to Kelvin, first change Fahrenheit to Celsius and then change it to Kelvin. Similarly, Kelvin to Fahrenheit, first we change from Kelvin to Celsius, you can see that here, and then to Fahrenheit. So that's how you convert from one to the other. It's you just have to put in the numbers carefully. But I want to tell you that there is one temperature on the Fahrenheit and the Celsius that are equal, and that number is negative 40. So negative 40 degrees Celsius is exactly equal to negative 40 Fahrenheit. You can try that, plug it in, you will get the same result for both. So here is a question that we should work out. showing you just how careful you got to be. So the question says, suppose a cold front blows into your locale and drops the temperature by 40 Fahrenheit degrees. How many degrees does the temperature decrease when it decreases by 40 Fahrenheit? So that's the part A. In this part, are we trying to change 40 Fahrenheit into Celsius? The answer is no. Because it says the temperature drops by 40 Fahrenheit. So that's the change in temperature. So the question here is, if the temperature changes by 40 Fahrenheit, how much will it change on the Celsius scale? So I'm going to do both. First, I'm going to show you how to change 40 Fahrenheit into Celsius. And then I will come to the actual answer of this question. All right. So if you had 40 Fahrenheit, how do you change into Celsius? Again, this is not the problem, what the problem is asking. So here is the formula. You would just plug in the value of T sub F as 40 and then calculate. So that will give 4.44 degrees Celsius. So 40 Fahrenheit is equal to 4.44 degrees Celsius. But this question is asking about a change. So what do? How much is a change of 40 Fahrenheit? Because we're looking for a change, we neglect the negative 32 part. That's all. We just go, oh, change in Fahrenheit is 40. What's the change in Celsius? All you got to do is multiply by 5, divide by 9, and you would get the answer as 22.22. So a change of 40 Fahrenheit is equal to a change of 22.22. So I hope you notice that difference right there. Moving on, the second topic here is expansion. We know that solids, liquids, and gases all expand when heated. And the expansion depends on three things. The expansion depends on the original dimensions, on the material, and on the change in temperature. So if you consider the length of a rod, how much it's going to expand depends on its original length. It depends on what material it is made of, which is going to be represented by a constant. And then third, it will depend on how much it is heated. So the formula for change in length of a rod is L alpha delta T. And you have the original length in meters. Alpha is called the coefficient of thermal expansion, which is either per Celsius or per Kelvin. And delta T, of course, is in either change, it's a change in temperature, so it could either be in Celsius or in Kelvin. So that's how, so what the picture shows is expansion gaps in a bridge in order to allow it to expand during summer. That's what you see here. The expansion gaps here. In summer, it expands and the gaps close. In winter, as it contracts, the gap widens. Now, if we don't have that expansion gap there, the bridge is going to buckle, it's going to warp, and there is going to be a problem. On the other hand, if we look at the change in area of a plate, a square plate, so if you have a metal plate, there's no meaning in talking about the change in length. In fact, both its length and its width changes, so that means its area changes. And the change in area is now given by this formula. You can see the difference is instead of alpha, you have 2 alpha. So that is what is to be noted. And then A is the original area, delta T is the change in temperature. When we come to change in volume, you can, this is more in relation to liquids and gases. All right, liquids and gases, they undergo a change in volume. So here you have beta times the volume times change in temperature. Now, beta is called the coefficient of volume expansion, the coefficient of volume expansion is 3 times alpha. So it is 3 times the coefficient of linear expansion. So if you're given the linear expansion of glass, so to say, and you're trying to find the change in volume of a glass bottle, you have to first multiply it with 3. So you get 3 alpha, which is beta, and then use it in this formula. So here are some values that are given. Here is a table. If you look at this table carefully, you would understand the values. So look at, on the left side, you have the coefficient of linear expansion. On the right side, you have the coefficient of volume expansion. Look at the first number. Aluminum is 25 times 10 to the negative 6, but volume expansion is 75 times 10 to the negative 6. So you see it's 3 times, okay? And again, the value of alpha is really, really small. It's 25 times 10 to the negative 6. So aluminum, oh, did I say aluminium? That's how the British say it. Aluminum has 25 times 10 to the negative 6. And then you can look down and you can see that lead has 29 times 10 to the negative 6. So lead expands more than aluminum. And when you come down, you can see all the values there. And then look at the value for concrete or brick. Why is it negative? Oh, so when you heat concrete or brick, it looks like instead of expanding, it contracts. That's why it's negative. And then if you look at the values for liquids, you only see coefficient of volume expansion there, like mercury, 180 times 10 to the negative 6, and so on. Okay, so that gives you a rough idea of the values of alpha and 3 alpha. Next up, let's discuss how water behaves when you heat it from 0 degrees Celsius up. So water is at 0 degrees Celsius at the freezing point. And when it is at the freezing point, we see that the density is less than 1. It's like 0.99985. So when you heat water from 0 degrees Celsius, its density increases. Wow, that means for a definite mass, the volume is decreasing, which is correct. That means when you melt ice, its volume decreases. When it becomes water, the volume decreases, so the density increases, and the density becomes maximum for water at 4 degrees Celsius. That's an important point. So the density of water is 1 gram per centimeter cube, or 1,000 kilogram per meter cube at 4 degrees Celsius. That is the temperature at which the density of water is maximum. And the maximum value is 1 gram per centimeter cube, or 1,000 kilogram per meter cube. Thereafter, if you continue heating water, it behaves like any other liquid. Its volume increases, therefore its density now decreases. So this is called the anomalous expansion of water. So, it's behaving extraordinarily, that's so to say, in this part from 0 to 4. All right, let's work out a problem on the volume expansion. So it says most cars have a coolant reservoir to catch radiator fluid that may overflow when the engine is hot. We have all seen that. There is a tank into which the overflowing coolant flows. The radiator is made of copper and is filled to its 16-liter capacity when at 10 degrees Celsius. What volume of radiator fluid will overflow when the radiator and fluid reach a temperature of 95 degrees Celsius? So it starts at 10 degrees Celsius and it's heated to 95. The beta, which is the volume coefficient of the fluid, is given. You can see that there. And then we also need the expansion of copper. We need which we will get from the table. Okay, it will be given to you. So two things expand here. the radiator, which is made of copper, expands, and also the fluid expands, the coolant expands, both expand. And we have to find out what volume will overflow. So how do you find what volume will overflow? Surely the fluid expands more than the radiator does. So what we'll do is we'll find out how much the fluid expands, then we'll find out how much the radiator expands, and then we'll subtract how much the radiator expands from what the coolant expands. So that'll give us how much overflows. So if, for example, it's not going to happen, but if both are expanded equally, then nothing will overflow. See? Because if the radiator expands as an equal amount as by the fluid, then nothing overflows. But fluids always expand more than solids. So the fluid is going to expand more, the radiator just a little bit. So to find how much overflows, we will take the difference. That is the idea here. So that's what we're going to do. So the C there is for the coolant. So change in volume of the coolant. We can keep it in liters. So 16 liter times the beta is 51 times 10 to the negative 6. Oh, wait. That is the change in volume of copper. So the C there, I'm sorry, stands for the radiator, for the coolant, because beta 51 is that for copper. So this is how much copper expands. All right, 0.069 liters. Because we have the original volume in liters, we get the expansion also in liters. Now let's find out how much the fluid, okay, the sub F there is for the fluid. The original volume is the same, 16 liters. Both the radiator and the fluid have the same original volume. There is the beta of the fluid. They both have the same change in temperature. When you make those calculations, you get 0.544 liters, which is obviously much higher than that of the radiator. So to find how much overflows, just subtract 0.544 minus 0.069, and that will be our answer. So 0.475 liters of the fluid overflows. Next, let's talk about an important constant called the specific heat. Specific heat actually shows the easiness with which a substance absorbs heat. For example, if you compare water and copper, and you heat them both on the same heat source, which one is going to get hot first? Or which one is going to have a faster increase in temperature? Definitely copper. Which means that the specific heat of copper is less. So what is specific heat? Specific heat is the amount of heat required to increase the temperature of 1 kilogram of any substance through 1 Kelvin. So if you have 1 kilogram of copper, 1 kilogram, and you give it a definite amount of heat, and its temperature increases by 1 Celsius or 1 Kelvin, that heat, the amount of heat that you gave, is the specific heat. For copper, it happens to be around 385 joules. So that's the specific heat of copper. Now, water has a very high specific heat, which means water doesn't get heated up fast. Neither does it cool fast. And the specific heat of water is 4186 joule per kilogram per Kelvin. I'm going to show you a whole table where the specific heats are listed. But before that, because of this definition of specific heat, we get a formula, which is Q is equal to mc delta T. Now, Q is the quantity of heat required to increase or decrease the temperature of a substance. So if you're giving heat, its temperature increases. If you're absorbing heat or removing heat, its temperature decreases. You can use this formula for heat gained or heat lost. And what is the formula? It's the product of mass, specific heat, and change in temperature. Mass, specific heat, and the change in temperature. And the change in temperature can either be in Celsius or Kelvin because the numbers will be the same. So let's practice that. But before that, here is the table that lists the specific heats. Take a look at it. There are two columns. On the left side, the unit is joule per kilogram. As you can see, it's joule per kilogram. But on the right side, it's kilocalories per kilogram. We'll get to that in a minute. So aluminum is 900. On the other side, it's 0.215. To change from joule to kilocalorie, you have to divide by 4,186. That's how you get 0.215. 4,186, okay? So we look at that left column, which is in joule per kilogram. You see aluminum has that 900, then copper is 387, like I told you. And you come down, the human body is about 3,500 at 37 degrees Celsius. So these specific heats depend on temperature, but we're not looking at that part. Water down there, you can see, is 4,186 and so on. So if the specific heat is big or it's a large number, the substance cools and heats slower. If the specific heat is small, it gets heated up or cools down faster. That's what you got to know. And here is a question. Before we work out that question, let's take a look at what the meaning of triple point is. First of all, this is a graph drawn with temperature on the x-axis and pressure on the y-axis. Unfortunately, the pressure is in atmospheres. Okay, so that's 1 atmosphere. And the temperature is in Celsius. So if you look at this graph, first of all, this line, it's called the fusion curve or the melting curve. So we're talking about ice and water. So at any point on this graph, you will have both ice and water. So that'll be exactly when ice is melting. If you decrease the temperature, which means move to the left side, even a little bit, you will only have ice. If you increase the temperature, you will only have water. So you see the L there for liquid and the S there for solid. So in this region, you have ice. In this region, you have water. So that's the melting curve. Similarly, you have the boiling curve here. So the boiling curve, you know that the boiling point of water is 100 degrees Celsius, yes, but that is if the pressure is 1 atm. That means if you increase the pressure of water, it's going to boil at a higher point, see, at a higher temperature. So as the pressure increases, the boiling point of water also increases. That's the advantage of using a pressure cooker. Because the steam gets collected in it, the pressure increases, so water boils at a temperature higher than 100 degrees Celsius, and by the time it boils, the food is cooked. So remember that the boiling point and the freezing point both depend on the pressure. So again, at every point on the left of this graph, it's water, but on the right side, it's a vapor or steam. And then you have the sublimation curve. You know what sublimation is? Where the solid directly changes into vapor without passing through the liquid phase. So that's a sublimation curve. And then at every point, here it's a solid, here it's a vapor. So you see the meaning of triple point now. All these three curves meet here or intersect there. That means solid, liquid, and vapor, all three coexist in what's called dynamic equilibrium. And that is at that pressure of 0.006 atm and 0.01 Celsius. That's the triple point of water. So when you specify the triple point, you have to talk about the temperature and the pressure. So the triple point of water is 0.01 degrees Celsius at a pressure of 0.006 atm. So I hope you get the idea of triple point. Shall we work out a problem using the concept of specific heat? Let's be careful on this one. Well, before we get to the problem, looks like we can't get to that. Before we get to the problem, let me also talk to you about change of phase. So if you take ice, and if ice is at negative 15 degrees Celsius, well, this graph talks about negative 20 Celsius, negative 20, and you start heating ice is not going to melt. Ice will only melt at 0 degrees Celsius at 1 atm. So assuming that the pressure is 1 atm, you have it at negative 20 and you start heating it, ice is not going to melt. Instead, the temperature of ice is going to go up as you give in more heat. Look, on the x-axis, you have heat supplied per mass. So that's for 1 kilogram. So as you first give heat, ice starts having an increase in temperature. But when it reaches 0 degrees Celsius, if you continue giving it heat, its temperature will not change now. Instead, it'll start melting. That's why the graph becomes horizontal, no change in temperature. You see the ice and the water there? That means it's a phase change. The solid is now changing into a liquid. But after all of that ice is changed into water, if you continue heating, now the temperature is again going to increase up until 100 degrees Celsius. And at 100 degrees Celsius, once again, there is a phase change. PHASE, phase change. The water is now changing into steam. Once again, the temperature is constant because you got water and steam. And then when all of the water has changed into steam, if you continue giving it heat, then steam is going to get superheated. Yes, so steam can be heated to a temperature more than 100 degrees Celsius. That superheated steam, in fact, that is what was used in the steam engine, the first engine to move. So remember that. So this curve, you should be able to understand this curve now. And now this diagram shows you why the temperature doesn't increase. During phase change, all the heat that is being supplied is used to break the molecular bonds. That's where it's going. And actually, it's called the latent heat. Latent heat. So you see, in a solid has a perfect structure, and the motion of the molecules is a minute vibration. So there is the limited motion. But when it becomes a liquid, the molecules are able to move further, more free, because the molecular bond strength has become less. And then when the liquid becomes a gas, oh, it's so free, the molecules just occupy every nook and corner of the container. So that's why the temperature doesn't increase, because all of the heat that the substance is absorbing during the phase change is being used to break the molecular bonds. And the formula for quantity of heat required is just the product of mass and the latent heat. For example, the latent heat of ice is 80 calories per gram. What does that mean? To change 1 gram of ice into water, it needs 80 calories. So what if you have 2 grams? Well, then it needs 160 calories. So to get the quantity of heat required in a phase change, just multiply the latent heat with the mass. If the latent heat is given in joules per kilogram, then the mass has to be in kilograms. Just be careful about that. Okay, in joules per kilogram, the latent heat of ice is big. It's 3.3 times 10 to the power 5 joules per kilogram of ice. You need not cram it. It's good to know the numbers. So here is a problem. Let me go back. Here is a problem. How much heat transfer is required to raise the temperature of a 0.50 kilogram aluminum pot containing 2.50 kilogram of water from 30 degrees Celsius to the boiling point and then boil away 0.750 kilogram of water. Okay. So what are we trying to do? We have 2.50 kilogram of water in a aluminum pot, and both are at 30 degrees Celsius, and we have to boil the water. So bring it to the boiling point and then boil off 0.750 kilograms. Right? So we don't have to boil off the whole water, so we just have to boil away 0.750 kilograms of water. So how do we do this? The specific heat of aluminum is given. It's 900 joule per kilogram per Kelvin. And the specific heat of water is also given. It will be a good idea to know it. It's 4,186. Same units. Since both have to be heated, let's first find the quantity of heat required to heat aluminum. Okay, so that's the mass of aluminum. Oh, I'm doing it together. So then you have the quantity of heat required to heat water. All right, so that is to heat water. And then you have a third part where you have to boil away the water. That's a phase change. That's why the formula now only has mass times latent heat. So the first part shows the amount of heat required to heat aluminum. Second part shows the heat required to heat water from 30 to 100. And then the third part shows how much heat is required to boil away the mass that is given. Okay, so plug in mass of aluminum is 0.75. 900 is the specific heat. And change in temperatures, 100 minus 30. Whenever you take the change, put the higher minus lower. Keep that in mind. Then mass of water, 2.50. Specific heat, same change in temperature. And then, here is the problem. This is where I made a mistake. First I thought all of the water was being boiled away. No, it's only a part that is being boiled away. So I had to go and change it. So here it is. 0.75 kilograms of water is boiled away. So that times the latent heat of vaporization of water, the latent heat of vaporization, because you're changing water into steam. So there are two latent heats. One is the latent heat when ice changes into water. That's called latent heat of fusion. The other is when water changes into steam. It's called latent heat of vaporization. Obviously, the latent heat of vaporization is much higher. Okay, so here we need the latent heat of vaporization, which will all again be given. So when you do the math, you get that big number, which is 2.47 mega, which stands for 10 to the power 6 joules. Then the B part says, how long does this take if the rate of heat transfer is 500 watts? Now, 500 watts means 500 joules per second. And so the power is given. So power is, we know, energy over time. Energy over time. So rearrange to get time as the subject. So you have energy over power. We got the energy required, which is the quantity of heat, divided by the power, and you will get the answer in seconds. You can change it into minutes or hours as you like, but that's how you do this problem. Hope that makes sense. Here's another one. If you pour 0.0100 kilogram of, that's a small amount. That's what, 10 grams. That's 10 grams of 20 degrees Celsius water. That's hot water. You're pouring a tiny amount of hot water at 20 degrees Celsius. Not very hot, but in comparison, it's hot. What are you doing? You're pouring it into a 1.20 kilogram block of ice. So you made a small hole in a block of ice and you're pouring this hot water, and ice is at negative 15 degrees Celsius. You're asked to find the final temperature. What is the final temperature? You may assume that the water cools so rapidly that effects of the surroundings are negligible. That means, just imagine that no heat is lost to the surroundings and no heat comes in from the surroundings, which is true in all of these problems. So here is the question. Is the entire block of ice going to melt? I don't think so. It's a huge block of ice. So first of all, what's going to happen is the hot water at 20 degrees Celsius is going to cool. It's going to cool 19, 18, 17. It's going to cool down. Let's assume that it cools to 0 degrees Celsius. Okay? Oh, and that means it gives out a certain amount of heat. Can we find that? Yes. We know the mass, 0.01. We know the specific heat, and we know the change in temperature. 20 minus 0. It's cooling from 20 to 0. So I'm talking about the hot water. We could find that amount of heat. That is the heat that's available in the hot water. And the ice is going to take that heat first, and then it's going to have an increase in temperature. So remember that from negative 15, the entire block of ice is going to go up from negative 15 to 0. It can't melt unless it reaches 0. You should be aware of that. So it takes a little part of that heat, that we get from the hot water, use that to take the temperature from negative 15 to 0. And if any amount of heat remains, that part of the heat will be used in order to melt the ice. So surely a certain amount of it's going to melt. Maybe it's going to melt. Let's find out. Let's do it step by step. So number 1, heat to raise the temperature. So I'm doing ice first. Okay. So to heat required to raise the temperature of ice from negative 15 to 0 degrees Celsius. MC delta T. Some people call it MCAT. So there it is. That's the mass of ice. The specific heat of ice is about half of that of water. It'll be given because we're not heating water, we're heating ice. And you get that number. So that's the heat required to raise the temperature of the block of ice from negative 15 to 0. And then the heat to lower water from 20 degrees Celsius to 0. Let's do that. I'm calling it Q1 is MC delta 1, delta T1. Yep, the mass is 0.01. Now it's water, so it's 4186. 20 minus 0 is 20. And we get 837.2. Oh, that's a tiny amount of heat. Next, we are finding out the heat lost to convert water into ice. So water is going to change into ice. And how much is that going to be? That is mass times latent heat. We have 0.01 kilograms of hot water, which is changing into ice. That's the latent heat of ice. So now the heat lost as you convert it into ice is there. So we got that. So what is the total heat that is lost? So remember that in these two processes, heat is lost. Okay, so the total heat lost to change water to ice. So I'm going to add these two. I'm adding these two quantities. This is actually 3,340. This is 837.2. If you add them, you get 4,177 joules. So that's the total heat lost. And this is the total heat gained. See that? This is the total heat gained. So let me pick this up from there. So surely the final temperature is less than 0 degrees Celsius. How do we know that? Look at this. The total amount of heat available is 4,177 joules. But to heat the entire block of ice to 0 degrees Celsius, you actually need a lot more. Isn't this like 37,620 joules? Yeah. You need a lot more heat. So that which means the temperature is not going to be more than 0 because the entire block of ice is not going to be heated up to 0. There's not that much heat available because of the little tiny amount of hot water that you poured. So continuing, heat lost, let's speed this up, heat lost by water is equal to heat gained by ice. So here we have heat lost by water. This is what we did before. I'm just writing that. But the difference you might see in this is, now watch, there are three processes there, but do you see that there is a question mark here? So we do not know the final temperature. We do not know the final temperature. Again here, we do not know what temperature ice reaches. If you've been listening carefully, you know that we could not reach 0 degrees Celsius. We could not. It's going to be some negative number. Well, surely more than negative 15, but not 0. We didn't have that much heat. So that's the unknown quantity here, okay, which you're trying to find. So I've taken the mass out because the mass is the same. Mass is the same. They're taken out, and then I've substituted this. This is 20 minus 0. Then you have the latent heat. You have the specific heat of ice and the change in temperature. Whenever you put the change in temperature, remember you got to put it as what? You got to put it as a higher minus lower, isn't it? So remember 0 minus TF and TF minus 15. So the question mark is TF. That's what I mean. So look at it carefully. That's the mass of ice, specific heat of ice, TF minus 15. So now it's the math part that you have to do carefully. So this one, you get a TF term here. You have another TF here. Collect those two terms. They add up and you get this as the total TF. And then collect these two. You add these two. And you will have to subtract this because it's a negative. So you have negative there. And then you divide to get the answers. Negative 13.22 degrees Celsius. So you may be thinking, why did I do it in two parts? See, I did this part just to show you that the entire block of ice could not be heated from negative 15 to 0. That's what I tried to show there. I tried to show that you need a lot more heat than is available. That's why I did that first part. And then I actually found that the final temperature is going to be negative 13.22 degrees Celsius. What do you mean? The hot water cooled to negative 13.22 and the ice that was at negative 15 got heated to negative 13.22. So all of them are now at negative 13.22 degrees Celsius. This is a tough question, but if you understand this, you should be able to do any question in this part, and that was my aim. All right, in the next section, we'll briefly talk about the three processes of transfer of heat: conduction, convection, and radiation. Conduction takes place in solids. Convection takes place in fluids. Radiation does not require a material medium. So the heat from the sun reaches the earth by radiation because there is miles and miles of space, which means there's no material. So you see all those three processes shown here. Conduction happens through the floor because that's a solid. Convection is where the hot air rises, you see, and the cold air comes down. You see the cold air and the hot air rising up through the chimney and out. And radiation is simply into the room. And that would have happened even if there was no air. So those are the three processes of transfer of heat. And we need to study conduction in detail. So if you take a rod and heat one end, you see that the quantity of heat conducted in 1 second, or in t seconds rather, quantity of heat conducted in t seconds is given by this formula Ka dt by dx. K is a constant which depends on the material. It's called thermal conductivity. You can see that there, thermal conductivity. A is the area of cross section or the area of contact. the area of the rod that is in contact with the heating source. So that's A. dt is the difference in temperatures between these two. According to this diagram, it is Th minus Tc. Th minus Tc. And the distance that separates them is dx or d. Okay, so I think you understood that. dt is the difference in temperature and dx is the distance between those 2 points. So dt by dx is actually called the temperature gradient. The temperature gradient. So we could work out a problem just to show you how this is practically applied. But here are some of the thermal conductivities. Diamond has a huge thermal conductivity. You see, 2000. Take note of the units. It's watt meter raised to minus 1. It should be actually meter raised to minus 1 and then Kelvin raised to minus 1, which is the same. It's given as watt per meter per Kelvin or Celsius, same thing. So diamond has 2000, very high thermal conductivity. That means it conducts a lot of heat fast. Okay, but when you come down to air, look at air. It's 0.023, right down there somewhere. Okay, which means air is a very bad conductor of heat. It's an insulator. Okay, so you have all those values there. Good. So here is a problem. Calculate the rate of heat conduction out of the human body. Assuming that the core internal temperature is 37 degrees Celsius, the skin temperature is 34 degrees Celsius, and the thickness of the fatty tissue between the core and the skin is on the average 1 centimeter. The surface area of the body is 1.40 meters squared. Very interesting. So the inside temperature of the body, inside the fat, is 37. That's the human body normal temperature. Outside, the skin temperature is 34, which means heat is being conducted through the fat out, right, to the skin, from the body to the skin, which you're trying to find out. So K of the human body is given. It's 0.2 watt per meter. That's the K of the fatty tissue, I must say. K of the fat, that's what is given. And then direct application of all these numbers into the formula will give you the answer. When it says calculate the rate of heat conduction, that means you have to find the heat conducted in 1 second. That's understood, 1 second. So time is 1 second. 0.2 times area is 1.40. 37 minus 34 by dx. What is 10 to the negative 2? Yeah, because it's 1 centimeter. You got to change it into meter. That's 1 divided by 100. That's why it's 10 to the negative 2. And we get 84 joule per second, which is 84 watts. So every second, 84 joules is being lost to the skin from the inside of the body. And that's why in order to maintain the temperature constant, we got to have to eat food. A part of the food that we eat is, of course, used to maintain the high temperature inside the core. Okay. It's understood. So here is another form of transfer of heat, which is radiation. Radiation of heat. So the amount of heat given out by a material depends on the material itself, which is characterized by what is called emissivity. Oh, I forgot to write that here. So actually the formula is going to be E sigma A. I missed out on the E. I'm going to write that down. So there's E. E is what is called emissivity. Excuse me. For a black object, E is 1. It's a perfect emitter and a perfect absorber. Black is a perfect emitter, so it has E is equal to 1. But white polished surfaces do not emit anything, so it's 0 emitter, so E is 0. So black, E is 1. White polished, E is 0. So E is emissivity. Sigma is a constant which is called Stephan's constant, and it's 5.67 times 10 to the negative 8. 5.67 times 10 to the negative 8. A. A is the surface area because it's this whole surface that's radiating heat. T1 is the temperature in Kelvin of the object, and T naught, again in Kelvin, is the temperature of the surrounding. If no mention is made about the surrounding, then take T naught as 0. Okay? But the temperature's got to be in Kelvin. Now, what is shown here is that if it's a black object, most of the heat is absorbed. A tiny, tiny part is reflected, which is basically 0%, So black. And look at when the black radiates, same thing. It retains a tiny part, it radiates all of it. It's emitting. So that's why it's a good absorber and it's a good emitter. That's black. When it comes to silver coated, which is white polished, most of it is reflected. See that? It doesn't absorb much and it doesn't radiate much. That's what I was talking about. Let's do a problem. So an infrared heater for a sauna has a surface temperature of 0.050 meters squared and an emissivity of 0.84. So the surface area is given, the emissivity is given. What temperature must it run at if the required power is 360 watts? Now, what do you mean by 360 watts? 360 joule per second. So you given Q by T. You know the value of sigma. So it's constant right there. Emissivity is 0.84. Temperature is what we are trying to find. We do not know that. So that's the area. So we do not know that. And it says neglect the temperature of the environment or the surroundings. So this thing is just neglected. It's 0. And then Q by T is 360. When you do these problems, you have to be careful. That applies to any problem. But here you have to take the fourth root. So be careful. Rearrange, take the fourth root carefully, and you get the answer as 623 Kelvin. That's the answer, 623 Kelvin. Okay, so I think this is where I'm going to stop on this video. So this is the first part of a 3-part review video for university physics students. But it's also going to help college physics 1 students. But basically, it's for university physics students. I hope makes sense. Be on the lookout for the remaining 2 parts of the review, and if you study all these problems, then you're going to do good on the final exam. Thank you. We'll see you in the next video.